The people at home have their Stoke slides out, but they also have this sheet from my previous lecture out because on the back is that helpful cheat stuff. But remember, if you go to the chemistry references folder on Canvas, you can find a link to a similar. It's not very often that someone says stoichiometry is their favorite thing. So, my apologies that you have to be good at this. But on the AP exams, the stoichiometry is embedded in several places. I also want to let you know that College Board believes that this is easy. They know how hard we hit it in honors. And when I say that they think it's easy, when I do train you on how to do your FRQs, there's a question with multiple letter parts, and from my experience, they try to make letter A the easiest part of the question to give you like a sense of, okay, I'm not going to drown, and then B and C become more challenging. But a lot of times that gimme, if you want to call anything that, is either a conversion or a stoichiometry question because they think that you can just do that. And I want that to be the case. So, do make sure that you're good at this. It's going to kind of feel like I go quick through it because what I'm about to show you was 4 lectures last year. 4 lectures. And we're going to knock it out in one. So, as I've said a million times already, go watch those honors lectures if this is too fast. But I mean, you've been tested on it. The funny thing about stoichiometry, though, in the honors course is that the test scores for this unit are very polarizing. There's a bunch of A's and there's a bunch of 40s and 50s. There's not a lot of grades in between because it's just so repetitive that you either can do all of them or you can't. But anyway, I'm going to go through all of it just fast. Ask questions. Stop me. You have the power to slow me down. In a nutshell, this word, stoichiometry, is what makes reactions worthwhile to study. Like, we can predict products all day long. If you react these, it's going to make these. Or we can balance them, add those coefficients. But in real life, it's the stoic that matters. Because stoichiometry says, or asks the question, hey, if you want to make this much stuff, right? We know that you can make it by mixing these. But what about the amount of it that you make? That's what's important, because all the things around you that chemistry has created has been measured out to perfectly work the way it works. If you're going to make an ibuprofen pill that's supposed to be 200 milligrams, it's not enough to just know what goes into making an ibuprofen pill. You have to know what amounts of what things to mix together. That's what this is. It tells you. It's pretty simple, actually, in terms of such a big thing. You pop in some numbers and it says you need this much of this much of this, and you'll make that 200 milligram pill. That cheat sheet walks you through the steps. I think the thing that gets confusing sometimes is sometimes you don't have to do all the steps. Depends on what units they give you and ask for. But I try to explain it wholly. So, here's what you need to know. To do a stoichiometry problem, you have to start with moles of reactant. That's the most important thing. You must have moles of the reactant in order to figure out how much product it's going to make. If they give you moles of reactant, that's great news. You can just immediately start going to product. But if they don't give you moles of reactant, they give you molecules. That's annoying because you have to have moles. So there's a first step that you can see on that paper that will convert you 2 moles of reactant if that's not what they started you with. Sometimes you do the first step, sometimes you don't. Step 2 is the one that you always do no matter what. Because step 2 is what we call the moles to moles, because it's where you cross the yield sign. It's the moles of reactant being changed to moles of product from one side of the arrow to the other that you always have to do. And it's moles to moles, but of different compounds. Reactant, product. And sometimes you end there if it wants moles. But if it doesn't, if it says what are the grams, then there's one more click. Because then once you have moles of product, you can go to you can go to any units of that product. Now, that was a lot of words, so we're going to put this all into practice, of course. You'll definitely want that reaction written down if you don't have it. All right, so let's revisit this steps. I don't know if everyone, like some of y'all that were good at this last year, you're going to still be good at it. Nothing's changed on stoichiometric steps, but I will refer to the steps. We've got this question that wants us to turn ethane into oxygen. So if you look at the balanced reaction down there, you have to have a balanced reaction, but I see coefficients, so I know it's balanced. But you can see that the ethane is a reactant. And if you're like, wait, I don't know what ethane is, you're right. Like, you're not sure that's called organic nomenclature. It's a naming system that you're not responsible for. But they like to do this a lot. They'll name something that you don't know what it is, but it will be in a reaction where you know what everything else is. And you can process and eliminate down. Because you know the oxygen, the carbon dioxide, and the water. Therefore, the ethane must be the C2H6. Anyway, it gives us 48.8 grams of ethane. This is dimensional analysis, so we'll start with our given in the top left square, and then we'll begin the fun. Is this good news or bad news, the fact that they started us with grams? It's bad. I mean, as far as, like, that felt very serious. Like, we're going to be okay. But if they don't start you with moles, then you have to do step 1 that's on that sheet. You must start with moles of your reactant. So if it had started us with moles, we wouldn't have to do anything there, but it didn't. So we're going to go from grams of the reactant to moles of the reactant. That is a sometimes step. Step 2 on that paper, you always do. You can never skip it because it's the bridge from one side of the arrow to the other. Moles of reactant to moles, yes, again, of product. Which product do you think I'm going to pick between the CO2 and the H2O? The H2O, because that's what it's asking for. Right? If you go back to the question, it says determine the grams of water. So it picked for us. That's the product we'll consider. I mean, it'll pinpoint one or the other. The only time it doesn't is if it's a limiting reactant problem, in which case you can pick any product you want, but you have to pick it twice. I'm going to get to that soon. But now, there's more bad news technically, because sometimes you can end here. If it asked for moles of water, our grid is done along the top at least. But it doesn't. What does this question ask for? It wants grams of water. So this is technically the hardest type of problem because it didn't give moles and it didn't ask for moles, so you had to do all 3 of the steps. All right. Now we can do our diagonal drags. We did a little bit of this last week. So I'm going to drag this to there, not the number, just the units. And I'm going to do those diagonal drags all the way across. All right, now we just need the numbers. Now, really, we've done the hard part. It's my opinion that if you get messed up in stoichiometry, it's in something that we've already done. So if you can set up the grid, you're usually in pretty good shape. Now, all these numbers are conversion factors. If you remember, we used our normal conversion factors last week, but we do have a funkier thing down here that is just for Stoic. So to describe this, in our grid, anytime it's not mole over mole, it'll be our normal black here conversion factors. Anytime it is mole over mole, it'll be the weird one that you see on the bottom there. So as you start here, it is not mole over mole, so I'll use the normal black conversion factors. For mole, you can see it's the number 1. For grams, you can see that it's periodic table. That's a molar mass. You don't have to dig it out if you don't want to. I've got all the values calculated because I believe you can do molar mass. But it's carbon plus 6 hydrogens on the table. And I get 72.15. No, I don't. It's a lie. And I get 30.07. My bad. But my next pair of squares is mole over mole. And when you're mole over mole, you go to the other helpful conversion factor, which are the coefficients of the balanced equation, looking at that mole ratio. So I'm looking at the coefficients, so examine over there. The coefficient of the water is 6, while the coefficient of the ethane is 2. Finally, our last square pair is not moles over moles, so we're back to the black data. Grams is periodic table. It's going to be 18.02 for water. Hydrogen plus oxygen is what that is. And for moles, it's 1. Hey, look here before you click clack away. Order of operations can mess with you here. It's my suggestion that you multiply all of those and then hit divide on your calculator. Don't hit enter. And then multiply all of those. However, you'll want to protect the denominator in parentheses. All right, you don't want to divide by 30 and then multiply by 2, right? You want to divide the whole top product by the whole bottom product. So see if you can get an answer. We're going to draw a card. Solve this grid. Sig figs always for stoichiometry. Yeah. Remember, sig figs are based only off the starting number, not the conversion factors. So 3 sig figs. What's the divide at the bottom? Multiply across the top, get a number. Multiply across the bottom, get a number. Divide the top by the bottom. Let's talk to somebody. Let's go over to cluster 2, seat 5. Again? 2, 5. What'd you get? You slid a decimal somewhere. Your numbers are right. Say it again. Did you say 8 point? Your decimal's just in the wrong place. Run it again so you can prove it. Someone tell me the right number. Or everybody say it. Yeah, 87.7. Or maybe it was in scientific notation. Is that what it was doing? Yeah, but that wouldn't slide the desk. Hey, what's the vocab term that describes that number at the end? A theoretical yield. You already wrote that on the previous slide, but it's important to note that the answer to a stoichiometric grid is a theoretical yield. Why do we call it that? Well, because we haven't done anything. If you're just running numbers on paper, it's all theoretical. It becomes actual if you're getting your hands dirty in a lab, but we haven't done anything. That's a combustion reaction. We didn't combust anything. Just theoretically, if we had this many grams of one reactant in excess of the other, you'll notice it ignored the other reactant. Then theoretically, we'd make that many grams. All right. Now, as I'm sure that you remember, or you were reminded when preparing your slides, there's a couple little twists on Stoic that are really important, but also very logical in regards to figuring out how much stuff is made. Because this is cool to know that if you start off with about 50 grams of the ethane, you'll make almost 90 grams of water at the end. It's the real deal. But a couple very real applications. The first one is limiting reactant. Limiting reactant is the idea where what if you have starting amounts of all reactants? In the problem we just did, one of the reactants was considered excess, meaning we didn't even look at one of them. We only studied a reactant that gave us a value. In a limiting reactant problem, you'll be given starting amounts of multiple reactants, and you'll need to figure out which one do you run out of first. Last year, I gave you an example in class where we made cake. It was fake cake, but I gave you the ingredients of cake and gave you trays of, well, ingredients. And there was a point during that exercise where I gave you 1,000 gallons of, not gallons, but 1,000 pounds of flour and 1,000 things of sugar and only 2 eggs. And it turns out that the eggs were the limiting reactant because even though you had so much stuff of the other ingredients, you ran out of eggs right away. And you could stop, and the cake stopped. So for a limiting reactant, what you do is, since you've got multiple amounts of your different reactants, is you run 2 grids and you figure out which one would make less cake. Whichever grid would spit out a lower theoretical yield would be, well, the real theoretical yield, because the higher number would be impossible because you'd run out of the other one first. We're going to put that into practice. The other twist was called percent yield. That green equation will be on your formula chart in later units, so you don't have to memorize it. Percent yield gives us an opportunity to figure out if we're good scientists, because while theoretical yields are fun to like plan how to create something, when you go and do it, it turns out that the actual amount you produce won't match the theoretical amount that you thought you would. You'll always make a little less, even if you're perfect, because we're human and we always lose energy to other sources sometimes. So my point is that when you're really doing the lab, there's actually 2 numbers to consider. The theoretical yield that you got when you ran stoichiometry, and then the actual yield that you got when you did the lab. Slightly different numbers. And if you plug those in, if you compared what you actually got to what you should have got, and you multiply by 100, it'll give you a percentage. And your hope is that you're in the 90s. You're a pretty good scientist if you get 90-something% of what you should have. Let's put that into practice with kind of a super problem, as I call it, that puts it all together. Now, I changed something, I'm sorry. See that yellow highlighter? That is different than what you copied down. Fix it. The yellow highlighter is a change I thought would benefit us. So change it in your spiral. Make sure you have that equation going. All right, let's do this. All right, we've got a reaction. It's balanced for us already, which is nice, but that's definitely not always going to be the case. It gives me grams of pentane, which is that first reactant, and moles of oxygen, the second reactant. So this is already different than the first problem, right? We have a starting amount of both reactants, which is a good indicator that it's going to be a limiting reactant problem requiring two grids. Now, there is a third number, though. But do you see how that third number, 250, is describing one of the products? When you have a starting number that's describing a product, that's usually a good indicator that that number is not going to go into a grid, that it will be used after the fact. That's actually an actual yield. If you look at the wording, see how it says 250 grams was made in lab? So there's context clues here that we have to refamiliarize ourselves with. But let's start with the values that describe reactants, because that's what needs to be converted over to products. So it looks like one of them is 238.7. 238.7 grams of the pentane. That's one of the givens. The other is 9.200 moles of oxygen. All right. A little split here so our eyes don't get confused. So we need to run two grids. Let's draw some cards to help with this first one. Let's do the whole first reactant by itself. So we can again prepare our fun. Hey, let's pick on somebody right away. Let's go over to cluster 4, seat 2. Hey, 4-2. I just want to know, what units do you think we should first go to right here? Moles is correct. That's a great answer. Moles of what? Anybody? The same thing, right? Because we know that our cheat sheet says we must start with moles of our reactant. And it tried to start us with grams. So I don't want grams of the reactant. I want moles of the reactant. And then we can go to what? Anybody? To moles. Don't skip step 2. The bridge from one side of the yield to the other is moles of reactant to moles of product. So it's going to be moles again. Hey, there's two products, CO2 and H2O. Which product do you think we should do? The reason CO2 is correct is because if you read the rest of the question, they went to CO2. Like they chose that product for you. Right? There it is. So again, you'll get better at context clues, but yeah, it talks about the carbon dioxide, not the water. So practice, practice, practice. But not only that, I'm getting attacked by a fly. Not only that for the context clues, what units of CO2 did they measure in the lab? Grams. So we don't get to end here like we could sometimes. We'll have to do step 3 on your cheat sheet where you go to another unit of the product. Let's drag all of our diagonals. Not the number, just the diagonal. Or just the units, I meant. All right, get them all dragged down. All right, let's draw a card. Let's go over to cluster 3. Seat 2. Hey, 3-2. What number do you think I should put in that square? A 1 is correct. The way that he knows it's a 1 is because it's not moles over moles, so he went to the conversion factors that are black. And for moles, it's 1. For grams, it's periodic table, which will be 5 carbons plus 12 hydrogens for a molar mass of 72.15. Let's go over to cluster 6. Oh, it's an empty cluster. Hey, Aspen, what number do you think I should put in that square? 5 is correct. You can pass the broom. Why is it 5? Because it is mole over mole. And when it's mole over mole, it's the coefficients. So just look at those balanced coefficients. For CO2, it's 5. For C5H12, it's 1 because there's no coefficient. Finally, the last pair of squares is not moles over moles, so we're back to the black. For grams, it says periodic table. CO2 is 44.01 if you add up his molar mass. And for moles, it's 1. Questions? All right, look here. Look here. Stop doing what you're doing. I know a lot of you are working ahead of me, and that's awesome. But here's what I want you to do now. I want you to find that answer, and I want you to do as good as you can do on this second grid. A couple things to remember about limiting reactant. The reactants are different. That's the whole point. It's a grid for each reactant, but the product has to be the same. Both grids have to go to the same product so that you get two answers that are directly comparable to each other. Careful. These units are careful. Call me over if you get stuck. I'll give you a few minutes. Solve both grids. I'm coming. What's up? Yep, because we have to go to the same format of those grids. What is this? Oh, drive. They need to erase the 250. No. Look. You see how the let's go to the very. See how the 238.7 is the pentane, the first reactant. You see how the 9.2 moles is the other reactant. All those are my givens. That 250 that you were about to use is not describing a reactant, so it's not going to be a starting. Yeah. So the one thing that you realize here is that the second one is actually starting in the master. So you're not going to have that square or that square. It's just that, but it's going to be 9.2, right? So then, yeah. So you just need so. Yeah, so you're starting. That's the first thing.
Because that's the coefficient. What do you mean? Mole over mole is coefficient. Wait, that put it on the bottom. Ah, damn it. That's okay. That's why. Well, yes, them switch. That would be right, wouldn't it? Sure. These two switch is right, right?
Wait, why are you switching?
Because I put
Yeah, it's. Yeah, you did this diagonal direction perfect. Yeah, CO2's 5 across.
all my work is right.
Let's go. Yeah, another one. Perfect. Very good. Now, you don't have to, but if you want to actually answer the question, you can do it. It's from the equation on the previous slide, but even solving those grids doesn't answer the question on the projector. But I'll give you a little more time. Some of y'all are still working.
Maybe
What's the actual?
I don't know.
Which one of the two is the actual yield?
Actual yield is a value that's found in lab describing a product. So, so between the two, it's whichever one is smaller. The limiting reactant value is the theoretical yield. The bigger number doesn't even exist.
That's the green. That's the start.
You're welcome to keep working, but I'm going to talk. When I solve that top grid, I get a value of 728 grams. All right, so there's a theoretical yield. But then it was time to figure out the other reactant. Now, luckily, they started us with moles, which means we get to skip step 1 from our cheat sheet. Because according to stoichiometry, once you have moles of your given, then you go directly to moles of the product, which has to still be carbon dioxide, right? Because we want both answers to be CO2. So it's still CO2. But this grid will be shorter because they started us with moles instead of grams. And that's what you have to kind of have on your radar. But once you have moles of the product, you can go to any unit of the product. And again, we want it to be the same as the other grid. Drag the diagonals. Moles over moles is coefficients. For carbon dioxide, it's 5. For the oxygen, it's 8. Not moles over moles is conversion factors. For grams, it's periodic table. For moles, it's the number 1. I'm sorry. If you run that grid, I get 253.1. All right, now here's where some of y'all paused and had to rethink about what this means. Remember, only the smaller number is the theoretical yield. right? The larger number you get during this limiting reactant process is impossible. We have nothing to do with it. This is the theoretical yield because oxygen is the the limiting reactant. All right? It didn't ask for limiting reactant, but the reactant that produces the smaller number in the grid is the limiting reactant. So oxygen is limiting. That's theoretical, but the question wanted percent yield. So now we're back to the equation from a little bit ago, where to find the percentage, how good did you do? It's actual divided by theoretical times 100. Actuals found in lab, and if you look back at the problem, you'll see that there is a number that we have not yet used, which is the number 250, because it flat out says that's the amount of product that was made in the lab, actual. So then we're going to go actual of 250 divided by theoretical of 253.1 times 100 for a final percent yield of 98.78. Were these scientists good? Yeah, they made almost 99% of what they were supposed to make.